Swayam Prabha. Digital India. Educated India.
In the last couple of classes, we have been discussing the random walk models to get the mean square end-to-end distance of a polymer chain. So, in the first type of models, we discussed the freely jointed chain and the one-dimensional random walk or a drunkard walk. And then in the last class, we looked at slightly more detailed models like two-dimensional random walk, then a more general z-dimensional random walk and so on. And then finally, we looked at the case where we disallow the folding back of chain onto itself. And then in all the cases so far, we saw that the relationship we get for the mean square end-to-end distance is basically proportional to the number of repeat units. Okay, so this is what do we have so far, and this relation seems to be quite universal given that we have done various types of models. Okay. So, now I want to extend the idea, try to put in more details into the model, try to make it look more realistic, and then come back and establish that it does not really matter, right. And that is the whole idea why the TWI models do work in polymer physics, because the results, the scaling laws are so simple, and it applies for such a variety of cases that many different models give you the same results. The reason why they work is also because it does not really matter how are we building the model. What really matters is what assumptions are going into the model. Okay. So, let us say like what was common in all the models that we discussed. Okay. So, first we assumed that the segments were uncorrelated, and then we said that the segments are somewhat correlated in the sense that the chains cannot fold back onto itself. The adjacent segments cannot be folding back to itself. Okay. But what you may have noticed is if I looked at correlations of this particular type, where Q characterize my distance along the contour, then this particular correlation always decays rapidly as Q increases. Okay. So, in the first two models, the freely jointed chain and one-dimensional random walk, except for Q equal to 0, this particular correlation was equal to 0. Even in the other two cases, the first one was the two-dimensional random walk, again Q was equal to 0, then in that case we had B square, after that it was 0. Then for the case when we do not allow for the folding back into 2D chain, then in that case it decayed something like this. So, as Z for Z higher than 2, this particular expression will always decay, right. So, now you can see like why Z equal to 2 is a special case, because if we do have a 1D random walk, and if I disallow folding back, then what you see is like you do form like a straight chain. So, for Z equal to 2 case, if I disallow folding back, then there is only one conformation of the chain, right. That goes against the idea that the chain can take many conformations. Okay. That does not happen for Z equal to 3 or higher, Z equal to 4 or higher, because in that case even if for a 2D walk, even if I fold back, I can explode in the other direction, I can again fold back here, explore other direction and so on. So, it need not be a straight line, right. So, only for Z equal to 2, there is a problem for z equal to 4, 6 and so on, we do not encounter this kind of a difficulty. Okay. So, this really works. So, now we will try to build a more elaborate model where we do make this particular assumption and try to establish that this is what that is central to all these models, and that is the reason why do we get these kind of scaling law. This, by the way, is referred as short range correlation along the contour. Okay. So, this is my contour. So, if I am going along the contour, then this is my distance along contour, and therein we say that there cannot be like a chain folding back into itself. So, by no means the models we have developed prevent a folding back after longer distances. For example, let us say the one here, there are two, there is a meeting point here, but the 2 points which are meeting are very distant along the contour. So, from here to here I am going like all this way to come back to the same point. The distance along the contour is high, and there is like a crossover of polymer chains or segments that is not being considered in all these models, that is allowed even when we allow for the case where the folding back is not allowed. Okay. So, let us elaborate on this idea more, and then we can talk about like what else can happen in the case of a polymer chain. Okay. So, we will develop a slightly more elaborate model, or a more at least seemingly realistic model. We will refer to that as freely rotating chain. So, now not only we prevent the next segment to fold back into the previous segment, we also say that the next segment has to be at an angle theta with respect to the previous segment, right. So, let us say this is my BM plus 1 and this is my BM, then this has to be at an angle theta. Okay. But that can be like within like a cone, right. So, it can really rotate like a cone around this, like this, while maintaining the same theta. So, it can take many possible values as long as the angle between the two remains the same. Okay. So, now if I look into this, if I try to average over all possible values of Bm plus 1 for a given value of Bm, what you can see is that all the components, let us say this is my x and this is my y for the moment, although this will keep on changing after every segment. So, if this is my x and this is my y, then the y components will basically cancel, because it is equally probable to have a bond vector in this direction and in this direction. The y components cancel in this case, but let us say if a bond vector is here, it is equally probable to have a bond vector there. If I look at these two vectors, the y components are cancelling, but the x components add up. Okay. But what we can see here is this must be equal to something like Bm multiplied by some cos theta, because this will be my the same vector reproduced here, the cos theta of it becomes that vector. Okay. So, now if I look at again the RE square, again as we have been doing for all the models, we have something like this happening. Now, this is now again correlated even for the values L not equal to m, and the correlation again will be something like this. So, I can write this is equal to, for L higher than m, I can write this as equal to average of BL, where I fix B1, B2 to BL minus 1 dotted with BM, and then this is equal to BL minus 1 cos theta BM, where this again has to be averaged for B1, B2 to BL minus 2. Similarly, continuing this, we will have like BL minus 2 here, but a cos theta squared there, and BM, this is like B1, B2, all these are being held constant, BL minus 3, and we can continue doing it until this becomes equal to BM, or we can continue until something like L minus Q is equal to M. At that point we stop, because Bm dot Bm is equal to B square. Okay. So, in general what you will have is a relation that goes like this. Something of this sort. Now, as long as the cos theta is not equal to 1, because for cos theta equal to 1 we will have like a straight chain, and in that case again there is no other conformation. But if cos theta is less than 1, then as we go to like higher powers of the cos theta, we will have like progressively smaller values. So, as L minus 1 absolute value increases, basically BL dot BM decays. Okay. Now, you can do the math again. Again we will have some sort of an infinite series. Again we make similar assumptions that we have made in the earlier case of the work on a lattice without folding back, and then you can again recover a relation that will basically be having one extra factor apart from MB square. Okay. So, let us try to do that. So, what we have is something of that sort, and again I take the approximation that this m value is very high. So, we can replace this particular sum by q from minus to plus infinity. And we will have something like okay. Again I am doing the same kind of approximation we had earlier. So, again we have like 2 multiplied by this. Again this is like geometric series. This will be equal to cos theta by 1 minus cos theta, and the result we will have is MB square 1 plus cos theta by 1 minus cos theta. Okay. So, let us like try to sum up all these cases that we have discussed, and then what we have seen is RE square first of all is always proportional to m. That really means RE square proportional to the number of repeat units, provided that every segment or a step correspond to certain number of repeat units. And then the other thing we have seen, if I look at the actual relation, I can write in this particular way, because keep in mind, like, what exactly was B? B was a parameter of the model. We did not take B from any kind of a polynomial property so far, right? B is like a model dependent parameter. So how much difference it make if I replace, for example, this entire quantity by some kind of a B effective square, right? It's anyway like a model parameter. That is a model parameter for a toy model we are developing, right? So then this will actually be the relation that we have got for all the models. So for 1D, my B effective was equal to some B. For 2D, this was equal to B. For the case of a freely jointed chain, this was equal to B. For the case of a freely rotating chain, this is something like B multiplied by square root of and then for the case of, we did two cases for a general ZD random walk. If it is with folding, then we had of course B, and without folding, it was B something like square root of Z by Z minus 2. Okay. So now let us try to see like what does this B mean. Of course, this B effective is a parameter, but M is also a parameter, because ultimately the number of segments I am choosing to represent the polymer chain is something that is a property of the toy model. This is not a property of the polymer chain. Okay. So let's start looking at like what does B and M represent, and how can we use that to represent different kinds of polymeric systems. Okay. So this is not really a completely a meaningless parameter. They do have certain meaning associated with them. So let's try to look at the significance of this small b and capital M. This small b is often referred as the Kuhn length. Okay. And then if I take small b as the Kuhn length, then M is something like the number of Kuhn segments. So the Kuhn length is, by the way, a theoretical construct. It is by a scientist named Kuhn, but we can associate certain kind of meaning to it by comparing two cases where I represent a polymer chain by fewer Kuhn segments, and another case we represent a polymer chains with more Kuhn segments. Okay. So let us say if I have a polymer chain and the same polymer chain, and in one case I take the Kuhn length to be rather high, in other case I take the Kuhn length to be somewhat smaller. Okay. This, by the way, is fixed length, excuse the drawing. So now I am representing this particular polymer chain by, I will use a different color. By this kind of the freely jointed chain, so as to speak. On the other hand, So, I am just drawing straight lines between every cone segment. So, this becomes my toy model, and going back, this becomes my actual polymer chain. And now you can see, since in the first case I use fewer segments to represent the polymer chains, in the second case I use more segments to represent polymer chains. If you remember, as I increase the number of segments, I will have more possible conformations. Okay. So, this will give rise to lesser number of conformation than second case. Okay. And we have already said that the number of conformation basically is related to the entropy of the polymer chain, and in turn it is related to flexibility. So, what this means is this will be less flexible. So, one is lesser flexible than 2. Okay. So, now what does it mean? So, let us say if we have two polymer chains, one of them is more stiff compared to the other. So, if I am trying to draw the toy model for both the cases, I will use more segments for the flexible case and less segments for the stiff case. Okay. You can think about an extreme when I use only one segment to model the polymer chains. I will use a different color here. So, let us say this blue line is my my toy model in the case where the cone length is taken equal to the contour length, where contour length is the entire length of the polymer chain. This is my contour length. So, if I take like very large value, what I get is like a rod. On the other hand, if I think of an other extreme where I make my cone length to be like extremely small, then I get my polymer chain that looks something like this. And so on, right. This is like having many cone segments. So, representation will look something like that. This one has more cone segments and this is lesser cone segments. Okay. The reason why I am saying that this will have more flexibility is also because every cone segment is in turn uncorrelated. Okay. So, if I have more segments, then the next segment is uncorrelated and so on. So, we have the correlation decaying at shorter distances along the chain. Okay. And that is why we are saying that it will be like much more flexible. Okay. So, we can associate these two concepts to the concept of stiffness or flexibility of a polymer chain. In fact, there is something else called the persistent length, which happens to be like half of the cone length in certain polymer theories, like the freely jointed case we have discussed. And this is an often used parameter to characterize the stiffness of a polymer chain, right. So, if molecule has a higher stiffness, it will have a higher value of persistence length, we also refer to as LP. If it has a lesser persistence length, that means the polymer chain is more flexible. So, for the same model, for the same toy model, I can associate different kinds of polymer flexibility by simply tweaking two model parameters, this M and B, the number of cone segments and the cone length, and by this way we can study polymers of different flexibility. So, now just to complete the exercise, if I want to look at the whole length of my fully stretched chain, if this chain become like fully stretched, it is a very less likely conformation, but it is indeed possible because the chain can take many conformation. There can be a case where the chain is fully stretched. So, in that case, the length of the polymer chain become equal to m multiplied by b, and this is what we refer to as a contour length. So, think of a small rope that is like this, and then you think of like stretching like this. So, this forms the case when it is fully stretched. That length is what is contour length. Other way to think about it, if I measure the distance along the rope, that will give rise to the contour length of polymer chain. So, I will stop with this. Thank you.